Hello everyone. In today's video, we're going to address topic 1.3, energy and equilibria in the IB Environmental Systems in Societies syllabus. I'm going to talk about thermodynamics, equilibrium, feedback, resilience, and tipping points, which are all important concepts in environmental systems and societies. One of the big ideas in this topic is that the laws of thermodynamics govern how energy flows through ecosystems and dictate its organisms' ability to do work. First, let's review the laws of thermodynamics, which are the fundamental principles that govern the behavior of energy in ecosystems. The first law of thermodynamics is the principle of the conservation of energy, which states that energy in an isolated system can be transformed, but it cannot be created or destroyed. You've probably encountered this in a chemistry lesson at some point. This means that the total amount of energy in a system remains constant, although it may change from one form to another. For example, in a food chain, the chemical energy stored in organic matter is transformed into kinetic energy, or movement, heat energy, or thermal energy, and other forms of energy by different organisms, but the total amount of energy does not change. The first law of thermodynamics allows life to exist on Earth because it implies that energy can be transferred from one system to another. For example, the Earth receives solar energy from the sun, which is the main source of energy for most living organisms. Without this input of energy from the outside, life on Earth would not be possible. The second law of thermodynamics states that the entropy of a system increases over time. Entropy is a measure of the amount of disorder or randomness in a system. An increase in entropy or disorder arising from the energy transformations reduces the amount of energy available to do work. This means that every time energy is transformed from one form to another, some of it is lost as heat or other forms of low-quality energy that cannot be used by living organisms. For example, in a food chain, only about 10% of the energy available at one trophic level is transferred to the next trophic level, while the rest is lost as heat or waste. This 10% rule is responsible for the structure of ecological pyramids, in which the top trophic levels contain less biomass than lower levels, and is why there are fewer organisms at higher trophic levels. The next significant idea in topic 1.3 is that an equilibrium is a state where there is no net change in a system over time. There are two types of equilibrium: static or dynamic. A static equilibrium is a state where there's no movement or change in a system at all. For example, a rock resting on the ground is in static equilibrium because there are no forces acting on it. It's not going anywhere, nothing is changing about it. A dynamic equilibrium, on the other hand, is a state where there is movement or changes in a system, but it's balanced by opposing forces or processes. For example, a pendulum swinging back and forth is a dynamic equilibrium because the gravitational force pulling it down is balanced or offset by the tension force holding the pendulum up. As an open system, an ecosystem normally exists in a dynamic or changing equilibrium, either in a steady state equilibrium or in one developing over time, such as in succession, which is what you see on this slide here. This dynamic equilibrium is maintained by stabilizing negative feedback loops, which we'll address in just a couple of minutes. A steady state equilibrium is a state where there are constant conditions and flows in a system over time. For example, a mature forest ecosystem is in a steady state equilibrium because there are stable populations and nutrient cycles within it. A succession equilibrium is a state where there are changing conditions and flows in a system over time until it reaches a climax community. A negative feedback loop is a process that tends to reverse the direction of the initial change and counteracts deviation from an equilibrium. The thermostat regulating indoor air temperature is a good example of a man-made negative feedback mechanism. When the air becomes too warm, the thermostat turns off the heat, causing a gradual drop in the temperature. When the temperature becomes too cool, the thermostat turns on the heat again, raising the temperature. This cycle repeats itself, maintaining a dynamic equilibrium around the desired temperature. Natural systems depend on negative feedback mechanisms for stability. For example, if the population of rabbits increases in an ecosystem, this will increase the predation pressure by foxes, which will reduce the population of rabbits back to its original level. This is a negative feedback loop that stabilizes the population size of the rabbits and maintains the equilibrium. A positive feedback loop is a process that tends to amplify the initial change and drive the system toward a tipping point where a new equilibrium is adopted. You can think of this as the snowball effect. As a small snowball rolls downhill, it picks up more snow, which makes it roll farther and faster, picking up more snow as it goes and growing larger and larger as it rolls. A classic example of positive feedback in natural systems is ice melt driven by climate change. If the temperature of the Earth increases due to global warming, this causes more Arctic ice to melt, which reduces the albedo or reflectivity of Earth's surface, so that Earth's surface then absorbs more solar radiation, and that increases the temperature further. This is a positive feedback loop that destabilizes the climate system and pushes it towards a tipping point. A tipping point is a critical threshold where a small change can have large and irreversible effects on a system. For example, if the temperature of the Earth rises above a certain level, this may trigger a runaway greenhouse effect that could make the Earth uninhabitable for most life forms. The permafrost time bomb is a classic example of this happening. This is a destabilizing positive feedback in Earth's climate system. Warmer temperatures will melt some of the permafrost, which leads to an increase in methane released into the atmosphere by decomposers. Because methane is a powerful greenhouse gas, it drives more warming, which then melts more permafrost, which releases more methane to drive more warming to melt more permafrost. Earth's climate systems contain many overlapping and interdependent feedback mechanisms, which is why climate science is so complex and why predictions about the future can vary so much. The resilience of a system refers to its tendency to avoid such tipping points and maintain stability. Resilience depends on several factors, such as diversity and the size of storages within the system. Diversity, of course, refers to the variety of components and processes within a system that provide redundancy and flexibility to cope with change. For example, an ecosystem with high biodiversity has more species that can perform different functions and roles, which can increase its resilience to disturbances. If one organism dies out or the populations decrease, other organisms are present to fill in that role. Note the number of alternative energy pathways in this food web representing Tanzania's famed Serengeti National Park. Each one of these lines represents a feeding relationship. And if you look at the herbivores here, you'll note that many of them feed on different groups of producers. That level of redundancy diminishes as we move up the trophic levels from producers to primary consumers to tertiary consumers and apex predators. The size of storages refers to the amount of matter or energy that's accumulated or stored within a system, and that can buffer against fluctuations. For example, an ecosystem with large storages of carbon or water has more capacity to regulate its climate and the hydrological cycle, which can increase its resilience to droughts and floods. Humans can affect the resilience of systems through reducing these storages and the diversity. For example, human activities such as deforestation, overfishing, Pollution and urbanization can reduce the biodiversity of an ecosystem, as well as the storages of biomass or water. That then makes those systems more vulnerable to disturbances and moving towards tipping points or a new equilibrium. The delays involved in feedback loops make it difficult to predict tipping points and add to the complexity of modeling systems. For example, the effect of greenhouse gas emissions on the climate system may not be apparent for decades or even centuries due to the inertia and lag time of the atmosphere and oceans. We're looking at turnover times of thousands of years and sometimes millions of years in these systems, which is why there are significant time lags. Those time lags make it challenging to forecast the future impacts of climate change and to take appropriate actions to mitigate or offset them or adapt to the changing climate. In conclusion, thermodynamics, equilibrium, feedback, resilience, and tipping points are essential concepts to master when studying environmental systems and societies. You'll encounter these concepts in all of the other topics that we're going to study. They help us understand how energy flows and transforms in systems, how systems respond to change and disturbance, and how humans can influence the stability and sustainability of systems. These next few slides will show some aspects of energy and equilibria that you should be able to apply in an ESS examination situation. You should be able to explain the implications of the laws of thermodynamics to ecological systems. This is something that comes up almost every year in ESS exams. You should be able to discuss the resilience in a variety of systems. You might be asked to compare the resilience of two different food webs, one of them being fairly simple, one of them being fairly complex, and identify that the complex one is more stable and more resilient. You may be asked to evaluate the consequences of different tipping points. And you may be provided with a graph or a diagram showing the various interactions and flows of energy and matter within a system. And based on that graphic, tasked to identify how a change in one part will change another part. If you found this tutorial helpful, please give it a like and consider subscribing to my channel. You can find more ESS information and resources at my website, www.mrcreamerscience.com, or by following me on the platforms X and Instagram. Thanks for your time. Happy learning.